Yeah, today I'm going to discuss about the problem from our first unit, magnetic circuits and magnetic materials. So here, iron rod of 1.8 centimeter diameter is bent to form a ring of mean diameter 25 centimeter, and it is wound with 250 turns of wire. A gap of 1 mm exists in between the end faces. Calculate the current that is required to produce a flux of 0.6 milliweber, and they've given the permeability of iron to be 1200. So the first thing is that you're supposed to write the given data. So here the iron rod, diameter of the iron rod is given to be, diameter of iron rod is given to be 1.8 centimeter, and then so which is equal to 1.8 into 10 power minus 2 meters, and then diameter of iron ring is 25 centimeter, so which is 25 into 10 power minus 2 meters. Number of turns is 250, and then air gap length of the air gap, that is LG, is 1 mm, which is 1 into 10 power minus 3 meters, and they've given the relative permeability. Relative permeability of iron 1200. So they have given an iron rod. So let us assume this is the iron rod which is having a diameter of 1.8 centimeter, but this iron rod has been bent to form a ring. So this becomes a shape like this. So there exists a air gap in between two faces, which is 1 mm. The length is given to be 1 mm. This particular diameter is 1.8 centimeter, and when it has been bent to form a ring, it becomes a ring. Its diameter is 25 centimeter. So we need to determine the current that is required, that produce a flux of 0.6 milliwebers. So whenever current flows through this particular iron core, a flux is established in this particular core. So flux value is given to be 0.6 milliwebers. The current I we need to determine. So we are supposed to determine the current. Okay. So here we know the formula phi is equal to Ni by S, where phi represents the flux, N is the number of turns, current we are supposed to determine, and S is the reluctance. So here this reluctance is nothing but total reluctance. Here we are having a air gap as well as the iron material, iron core. So in that case, the total reluctance represents SI, that is length of the iron rod as well as the length of the air gap. Since it is having a both air gap as well as length of the, what is it, reluctance, we need to determine reluctance of the iron rod as well as reluctance of the air gap. So from this you can determine I is equal to, so when this becomes total reluctance, so this becomes phi into St whole divided by N. So I we are supposed to determine phi is known to you, that is 0.6 milliwebers. St is equal to Si plus Sg, where N is the number of turns. So in that case, so Si formula is Li divided by mu naught mu r into A. So Li, length of the iron rod is not known to us. Mu naught is 4 pi into 10 power minus 7. Mu r relative permeability is given to be 1200. A is the cross-sectional area, that is also not known to us. We need to determine. And then Sg is equal to Lg divided by mu naught mu r into A, that is cross-sectional area of your iron rod. So Lg, that is given to be 1 milliweber. Mu naught is 4 pi into 10 power minus 7, and mu r, that is for a air gap it is 1. So here also area is not known to us. So in that case we are supposed to determine the, first we need to determine length of the iron rod. So length of the iron rod. So length of the iron rod becomes 2 pi r minus length of the air gap. So length Li becomes 2 pi. So R value is, so diameter of your iron rod, that is your ring, that is 25 into 10 power minus 2, that is your diameter, divided by 2 gives your radius. So 2 pi 25 into 10 power minus 2 divided by 2 minus length of the air gap, that is 1 into 10 power minus 3. So this length of the iron rod becomes 0.784 meters. So when you calculate this, you'll be getting your length of the iron rod to be 0.784 meters. Similarly, you don't know what is your cross-sectional area. So area of cross-section that is A becomes pi r square. So this is pi, that is your diameter of your iron rod is given to be 1.8 into 10 power minus 2. So this becomes 1.8 into 10 power minus 2 whole square divided by 2. So cross-sectional area becomes 2.5 into 10 power minus 4 meters. So we know what is your area as well as the length of the iron rod. So we can easily determine what is the reluctance of your iron rod. So Li divided by mu naught mu r into A. So in that case, your Li is 0.784 divided by 4 pi into 10 power minus 7 into mu r is 1200, that into 2.5 into 10 power minus 4. So my SI becomes 2.08 into 10 power 6 ampere turns per meter. Okay, similarly SG, that is reluctance of your air gap, is Lg divided by mu naught mu r into A, which becomes Lg is 1 into 10 power minus 3 divided by 4 pi into 10 power minus 7 into 1 into 2.5 into 10 power minus 4. So this becomes 3.183 into 10 power 6 ampere turns per meter. So from this you can determine your SG. So SG becomes 3.183 into 10 power 6 ampere turns per meter. So already you know the formula, that is phi is equal to Ni by St, where St is equal to Si plus Sg. So we know what is Si as well as Sg. So your total reluctance becomes 2 point, that is Si plus Sg becomes 2.08 into 10 power 6 plus 3.183 into 10 power 6. So your total reluctance is 2.08 plus 3.183. So this becomes 2.08 plus 3.183 becomes 5.2. Total reluctance is 5.263 into 10 power 6 ampere turns per meter. So from this we can easily determine the current. So my current equation becomes total reluctance into phi divided by number of turns. So this is 5.263 into 10 power 6 into 1 into 10 power minus 3 whole divided by number of turns is 250. So this becomes, your I becomes 12.63 amperes. So this is how we are supposed to solve this problem. That is, we are asked to determine the current that is required to produce a flux of 0.6 milliweber. So in that case, my current becomes 12.63 amperes. So we require 12.63 amperes to produce a flux of 0.6 milliweber when a rod has been bent to form a ring with a diameter of 25 centimeter. Is that clear? Okay. So next. So next will be given a next problem, that is, so here that is reluctance, it is ampere turns per Weber. So next we'll move on to the next question, that is for a magnetic circuit. So next problem is for the magnetic circuit that is given over here. Magnetic circuit that is given over here is having a thickness of, is with a core having a thickness of 5 centimeter, exciting current 0.5 amps with 1000 turns coil. Find the flux density and flux in each of the outer limbs and central limb. Assume relative permeability for iron of the core to be infinity, that is first subdivision is infinity, second one is 0. $4,500. So the figure is so it will be given a 2 limbs as well as central limb. So in the outer limbs you are given a air gap of 1 mm. Here air gap of 2 mm. So here we are having a coil which is excited by a source. So this is 5 centimeter. So this is B point, this is your A point. So this is 30 centimeter. This particular length is 40 centimeter. This is 30, this is 40, and this is 10 centimeter. This is 5 centimeter. Okay. So here they given a problem for a magnetic circuit which is having a core of thickness 5 centimeter, exciting current of 0.5 amps with 1000 turns coil. Find the flux density and flux in each of the outer limbs and a central limb. Assume the relative permeability of iron of the core to be infinity. The first case is infinity, second one is 4500. So first we'll write the given data, that is our LG1. Let us assume this is to be the first limb, this is second limb, and this is my central limb. This is my central limb. So here first write down the given data, that is LG1 is, that is length of the air gap is 1 mm, length of the air gap that is on the outer side, that is the second side is 2 mm, and then so whenever this is excited by the source, the current flows through your coil. The number of turns is given to be 1000. So here it is 1000 turns. Number of turns is 1000. And then, so when the current flows through this particular coil, the flux is going to get established in the outer limbs. So it flows in this so it is going to get established in this manner. So this is phi 1, this is phi 2. So let us assume the total flux to be phi t. So the area we need to determine. So here the area is area 1, which is equal to area 2, that is cross-sectional area of the outer limbs, area 1 as well as area 2 is 5 into 5 into 10 power minus 4 meter. So this becomes 1 into 10 power minus 3 meter, and your length of the air gap on the outer limb second side becomes 2 into 10 power minus 3 meter, and your cross-sectional area of the area 1 as well as your area 2 becomes 5 into 5 into 10 power minus 4 meters square. And then let us move on to the first case where the relative permeability, that is case 1, where relative permeability is given to be infinity. Relative permeability of iron core is given to be infinity. So we know the formula, that is reluctance is equal to L by, this is the generalized formula, mu naught mu r into A, or else we can say that my reluctance is inversely proportional to relative permeability. So here this relative permeability is given infinity. In that case, my reluctance of the iron core becomes 0. So outer limb is going to have a reluctance, that is first limb as well as the second limb is going to have the reluctance to be 0. So it is going to have only the air gap. Reluctance of the air gap is alone present over here. Okay, reluctance of the iron core is 0 in case of in outer limbs. It is going to have only the reluctance in the air gap alone. So when you draw the equivalent circuit, we'll be getting a equivalent circuit like this. So this is the equivalent circuit. So this is SG1, which we are supposed to determine. This is SG2, and this is my MMF. So this is phi t total reluctance, this is phi 2, and this is phi 1. So here, when you see the equivalent circuit, it is not having the reluctance of the core because they have given the relative permeability to be infinity. In that case, the reluctance of the iron core becomes 0. That's why I have not given any reluctance in the limbs. Either it is a outer limb or a central limb, there is no reluctance in the iron core. It is having only the air gap in the outer limbs. Almost there is no air gap in the central limb. Okay. So in that case, we are supposed to determine the flux density. Flux density. So flux density formula is flux per unit area. So area is known to us, phi is not known to us. So again we can go for a Ohm's law of magnetism where this phi is equal to Ni by St, where we are supposed to determine the total reluctance. So St here becomes, that is Sg1 plus Sg2. So my Sg1 is Lg1 divided by mu naught mu r into A. So here Lg1 is 1 into 10 power minus 3 meter divided by 4 pi into 10 power minus 7. Mu r is 1. Area is 25 into 10 power minus 4. So my Sg1 becomes, Sg1 is 1 into 10 power minus 4, 4 pi into 10 power minus 7. Yeah, let me do this. 1 exponential minus 3 whole divided by 4 divided by 4 pi into 25 exponential minus 4. Point 03183 is, so 1 exponential 3 divided by 4 pi into 25 exponential minus 4. This becomes 0.0318. 0.03183. That is ampere turns per Weber. Similarly, Sg2 becomes Lg2 divided by mu naught mu r into A, which is 2 into 10 power minus 3 whole divided by 4 pi into 10 power minus 7 into 1 into 25 into 10 power minus 4. So here it is Sg2 is 2 exponential minus 3 divided by 4 pi. I think here it is 10 power minus 7 is missing. So we'll be getting so that is 2 exponential minus 3 divided by 4 pi exponential 7 minus 7 into 25 exponential minus 3. You can take this. So here it is into 10 power minus 7. So this becomes, just cross check this answer. Similarly, here you will be getting 1 into 10 power minus 3 divided by 4 pi into 10 power minus 7. SG2 value is ampere turns per Weber, which is equal to 0.636 into 10 power 6. Here it is, SG1 is 0.318 into 10 power 6. 0.3. Okay. So this is, SG2 is 0.063 into 10 power 6. SG1 is 0.318 into 10 power 6 ampere turns per Weber. So now you can calculate what is ST. Yeah. So this is 0.06 into 10 power 6 ampere turns per Weber, and ST is SG1 plus SG2. So this becomes 0.3183 into 10 power 6 plus 0.63 into 10 power 6, which becomes 1.318 exponential 6 plus 0.63 exponential 6 becomes 0.954 into 10 power 6 ampere turns per Weber. So now you can easily determine your phi 1. So phi 1 becomes Ni divided by S1, Sg1, which becomes N is 1000 into current is 0.5, that is 0.5 whole divided by Sg1. Sg1 is 0.3183 into 10 power 6. So phi 1 becomes 0.785 into 10 power minus 3 Webers. Similarly, phi 2 becomes Ni divided by Sg2, which is equal to 1000 into 0.5 divided by 0.63 into 10 power 6. So my phi 2 becomes 1.571 into 10 power minus 3 Webers. So now I can easily determine the so flux value is known to us. So we need to determine the flux density B1. B1 is phi 1 divided by A1, which is phi 1 is 0.785 into 10 power minus 3 whole divided by area. Area is 25 into 10 power minus 4. So my flux density becomes 0.314 Weber per meter square. Similarly, B2 is phi 2 divided by A2. Phi 2 value is 1.571 into 10 power minus 3 divided by 25 into 10 power minus 4, which becomes 0.628 Weber per meter square. So now we know what is the flux density that is there in the outer limbs as well as flux in the outer limbs. So now we are supposed to determine the total flux so that we can determine what is the flux density in your central limb. So phi t is equal to phi 1 plus phi 2, that is 0.785 into 10 power minus 3 plus 1.57 into 10 power minus 3. So this becomes 1.2.356 into 10 power minus 3 Weber. Similarly, the flux density, that is flux in the central limb, is going to be total flux, that is phi t divided by area. So here the area of the core. So the area of the core we need to calculate. So this becomes AC is 10 into 5. 10 into 5 into 10 power minus 4 meter square, because here they have given this particular width to be 10 centimeter, and this particular width is given to be 5 centimeter. So 10 into 5 into 10 power minus 4. So your entire flux becomes 2.35 into 10 power minus 3 whole divided by 10 into 5 into 10 power minus 4. So this becomes 0.471 Weber per meter square. So far we have just calculated the flux as well as the flux density in the outer limb as well as the central limb when the relative permeability is given to be infinity. So now we can move on to the second subdivision where the relative permeability is given 4500. So the second case 2 is the relative permeability of the iron core. Relative permeability of the iron core is given to be 4500. So here when you draw the equivalent circuit, you'll be getting a, so since the relative permeability is not infinity over here, you'll be getting the reluctance also. So reluctance will be present in the outer limbs, here first limb as well as the second limb, as well as you'll be having the reluctance in your central core. So in that case, you'll be having, you need to find the reluctance of the iron as well as your air gap. Similarly, here also you need to determine the reluctance of the iron rod, that is your core, as well as your gap. So here in that case, my equivalent circuit becomes like this. So this is my equivalent circuit where this represents SI1, that is reluctance of the iron core, reluctance of the air gap. This is my source where I am having the reluctance of the core. Here also reluctance of the iron path, that is I can assume this to be SI2, and then this is SG2. So let us assume this S1, this is my first limb. So in that case, S1 is nothing but SI1 plus SG1. Similarly, S2, that is my second limb. This is my second limb, outer limb. So here this becomes SI2 plus SG2. And this is my central limb where the central limb SC is assumed to be SC. So this is my flux phi t. So the flux that is flowing established in this particular path is phi 2 and this particular path is phi 1. This is SC. Okay, so now we need to determine S1. So here also the same thing we are supposed to determine, that is flux density in the outer limb, outer two limbs as well as the central limb. So in order to determine a flux as well as flux density, let us determine the reluctance, that is reluctance in the outer limb 1. So S1 is SI1 plus SG1. So SG1 is already known to us. Now we need to determine SI1. So SI1 is Li1 divided by mu naught mu r into A. So we don't know what is this Li1. So this Li1, that is outer limb length of a outer limb length, that is first limb as well as the second limb, is going to remain same. So in that case, my Li1 is equal to Li2, which is, so this particular length is given to be 40, this is 30, this is 5, 10. So in that case, 40 plus 2.5 plus 2.5 plus 30 plus 2.5 plus 5 plus 30 plus 2.5 plus 5. So my Li1 becomes 120 centimeter. So everything in centimeter. So my Li1 that is equal to Li2, that is length of the outer limb, is 120 centimeter. So knowing the length, we can easily determine the SI1. So my SI1 becomes 120 into 10 power minus 2 divided by, that is meter, divided by 4 pi into 10 power minus 7. My mu r is 4500 into area. Area here is 25 into 10 power minus 4. So my SI1 becomes 0.085 into 10 power 6 ampere turns per Weber. So my SG1, so already we have calculated SG1. So SG1 is LG1 divided by mu naught mu r into A. So already we have calculated this particular value is point. So LG1, so 1 into 10 power minus 3 divided by 4 pi into 10 power minus 7 into 1 into 25 into 10 power minus 4. So my SG1 is 83. One second. So this is what previously we have calculated, that is 0.3 into 10 power 6, 0.38 into 10 power 6 ampere turns per Weber, right? So SG1 is 0.38 into 10 power 6 ampere turns per Weber. SI1 is 0.085 into 10 power 6 ampere turns per Weber. So when you add these two things, so it would be around 0.085 into 10 power 6. That is S1 is SI1 plus SG1. That's why 0.085 into 10 power 6 plus 0.38 into 10 power 6. So my S1 becomes 0.403 into 10 power 6 ampere turns per Weber. So similarly, so now you know what is your S1. Similarly, we need to determine what is my S2. So here S2 is again SI2 plus SG2. So you know what is SI2? So SI2 is LG2 divided by mu naught mu r into A. So LG2 is 120 into 10 power minus 2 meter divided by 4 pi into 10 power minus 7 into 25 into 10 power minus 4 into 4500. That is relative permittivity. So my SI2 becomes same thing. That is since both Li1 as well as Li2 is same, my SI2 as well as SI1 is going to be the same answer, that is 0.085 into 10 power 6 ampere turns per Weber. Similarly, my SG2 is LG2. The first subdivision itself we have determined this, that is LG2 divided by mu naught mu r into A, which is 2 into 10 power minus 3. So you can use the previous data which we have determined already, that is into 1 into 25 into 10 power minus 4. So my SG2 becomes 0.636 into 10 power 6 ampere turns per Weber. So we have determined what is SG2. So now my S2 is SI1 plus SG2. SI2 plus SG2. So this becomes 0.085 into 10 power 6 plus 0.636 into 10 power 6. So my S2 becomes 0.40, 0.7216 into 10 power 6 ampere turns per Weber. So far we have determined what is my reluctance in the first limb, reluctance in the second limb. So reluctance in the first limb is calculated to be 0.403 into 10 power 6 ampere turns per Weber. Similarly, reluctance in the second limb is calculated to be 0.7216 into 10 power 6 ampere turns per Weber. So now you can easily determine what is my phi 1. So I am just having this S1. So just note down this S1. S1 is 0.403 into 10 power 6 ampere turns per Weber. Similarly, my S2 is 0.7216 into 10 power 6 ampere turns per Weber. So knowing these two values, so keep it as such. So similarly, we need to determine what is the reluctance in the core. So reluctance in the core formula is SC. So SC is again, reluctance in the core is LC divided by mu naught mu r into A. So this becomes, length of the core is given to be 40 into 10 power minus 2, 4 pi into 10 power minus 7 into 4500 into this particular area is 10 into 5 into 10 power minus 4. So my SE becomes, okay, just to calculate this. So my SE becomes 40 exponential minus 2, 0.016 into 10 power 6 ampere turns per meter. So my SE is also known. So yeah, ampere turns per Weber. 0.016 into 10 power 6 ampere turns per Weber. So now we need to determine what is the flux that is there on the, that is established in the limb 1, flux that is established on the limb 2, as well as total flux. So phi formula is known to us. Phi is equal to Ni by S1. So phi 1 is Ni by S1. So N is 1000 into current is 0.5 divided by S1 is 0.403 into 10 power 6. So this becomes 1000 into 0.5 divided by 0.403 exponential 6. So this becomes 1.24 into 10 power minus 3 Webers, right? So B1 becomes phi 1 divided by A1, right? So what is my area? So 1.24 into 10 power minus 3 divided by, my area is, cross-sectional area of the first limb becomes, what is that area? I have given 25 into 10 power minus 4, right? So B1 becomes divided by 25 exponential minus 4. 1.24 into 10 power minus 3 divided by 25 0.496. What is the 5 flux you are getting? 51. Point 51 is 0.78. 1.24 into 10 power minus 3. So 1.24 into 10 power minus 3 divided by 25 into 10 power minus 4. Flux is 1.24 into 10 power minus 3 divided by 25 into 10 power minus 4. 0.496. Just check it out, 0.496. Similarly, your phi 2 is, that is 1000 number of turns into 0.5 divided by your S2. 0.7216 into 10 power 6. So phi 2 becomes 1000 into 0.5 divided by 0.72 into 10 power 6. 6.9. Other paper. Just check it out, phi 1 as well as a phi 2. Phi 1 is 0.496 Weber per meter square, and then phi 2 is 6.9. Phi 2 is 6.94 Weber per, sorry, this is Weber. And then similarly, you can determine your flux density. So flux density becomes phi 2 divided by your area, that is your area of the second limb. So phi 2 is 6.94. This is into 10 power 4 into 10 power 4 Weber into 10 power minus 4 divided by 25 into 10 power minus 4. So B2 becomes 0.27 Weber per meter square. So now we know what is the flux density in the first limb, that is the outer limb 1, and the second outer limb. Now we need to determine what is the flux in the central core. Or else you can add these two fluxes, phi 1 as well as phi 2, which gives your entire flux, that is your total flux. So phi 1 plus phi 2. So what is my phi 1? My phi 1 is 0.48 or whatever it is. 1.23 into 10 power minus 3 minus 4 plus 6.94 into 10 power minus 4. So you can easily determine your total flux. So my total flux is 1.9319 into 10 power minus 3 Weber. So my flux density in the central core becomes BC, that is total flux phi T divided by the cross-sectional area of the central core. So this is 1.932 into 10 power minus 3 whole divided by 50, that is 10 into 5, 50 into 10 power minus 4. So flux density in the central core becomes 0.386 into 10 power 0.386 Weber per meter square. So this is how you can determine your flux as well as the flux density in the outer limbs as well as the central limbs when you are given relative permeability of the iron core to be infinity, as well as relative permeability of the iron core is given a value of 4500. So with this, let me move on to the second unit. where you are given a transformers. So as we all know, transformer is a static device which is going to convert energy, that is voltage, from one circuit to the another circuit without changing frequency. So in that case, you'll be given a transformer like this, where we have a primary winding which is connected to the source, and the secondary winding, when it is connected to the load, the flow of current will be there. So let us assume that to be I2, and current that is there in your primary winding is I1. So whenever there is a flow of current in the primary winding, the flux is going to get established in your core. So in that case, when I am moving on to the equivalent circuit of a transformer, this is how this is how you'll be representing a transformer, where you will be given a primary winding, secondary winding. The primary winding is connected to the source, the secondary winding is connected to the load. So when you move on to the equivalent circuit of a transformer, it is assumed or imagined you will be given a resistance as well as a reactance, which is given externally to the winding. So you'll be given a primary resistance as well as a reactance, that is leakage reactance will be there. And then secondary side also will be given a resistance as well as a reactance. So this resistance as well as a reactance which has been present externally to the winding helps in transferring energy, that is voltage, from one circuit to the another circuit. So in addition to that resistance that is there on your primary winding as well as on the secondary winding, you will be given a no load circuit. So here this is my no load circuit, which is having a current of I naught, which has been resolved into two components. Resolved into two components, that is IW and then IM. So this is I1, here the current flowing is I2 dash, here it is I2, here you'll be given a source of V1. You, this is induced EMF V1. I'm just redrawing the circuit. So you'll be given a resistance as well as magnetic leakage reactance, that is R1 as well as X1, which is imagined to be present externally to the windings, that is primary winding and secondary winding. So the resistance as well as the reactance on the secondary side is assumed to be R2 as well as X2. The load is given ZL. So in addition to the primary windings R1 as well as X1, you will be given a no load circuit, so which takes a current of a no load current I naught, which has been resolved into two components IW as well as IM. So this IW, so this is IW as well as IM. IM is the working component which is meant for core loss, that is occurring in your primary side, core loss. Okay, so this takes care of a core loss that is occurring in your primary side circuit, and then IM is the magnetizing component which is used to establish a flux in the core, which is used to establish a flux in the core. So whenever current flows through this primary side, EMF is induced on your primary side. Let us assume that to be E1. So this is going to get links with your secondary side because of a mutual induction principle. EMF is going to get induced on your secondary side. Let us assume that to be E2. And then voltage that is there on your load terminal is V2, right? So when you see this circuit seems to be somewhat complicated. So it is not that much easy for us to solve this complicated circuit. So now we are supposed to transfer, in order to reduce the complication, we are supposed to transfer either the secondary side parameters to the primary or a primary side parameters to the secondary side. Either you can transfer primary side parameters to the secondary side or secondary side parameters to the primary side. So in that case, your primary equivalent of secondary side resistance becomes R2 dash, which is R2 by K square. Similarly, primary equivalent of secondary side reactance is X2 dash, that is X2 by K square. Similarly, primary equivalent of secondary side load impedance ZL is ZL dash, which is ZL by K square. And then where this K is transformation ratio, which is E2 by E1 or N2 by N1. Similarly, you are having V2 dash as well as E2 on your secondary side. So in that case, the primary equivalent of secondary side EMF E2 becomes E2 dash, which is E2 by K. E2 by K. And then primary equivalent of secondary side terminal voltage. Secondary side terminal voltage is V2 dash, that is V2 by K. And then I2 dash, the current, primary equivalent of secondary current. I2 becomes I2 dash, which is I2 dash is I2 by K, where K is a transformation ratio, right? So primary equivalent of secondary side resistance, that R2 becomes, when you transfer to the this particular side, primary side, this becomes R2 dash, that is R2 by K square. Similarly, when X2 is transferred to the primary side, this becomes X2 dash, that is X2 by K square. And then your load impedance ZL, when it transferred to the primary side, this becomes ZL dash, that is ZL by K square. And then your transformation ratio is E2 by E1 or N2 by N1. And then when similarly you can transfer E2 as well as V2 to the primary side, that is E2 by when this E2 is transferred to the primary side, this becomes E2 dash, so E2 by K. Similarly, when your voltage, that is secondary side voltage, is transferred to the primary side, this becomes V2 dash, that is V2 by K. And then I2 dash, when it is transferred to the primary side, this becomes I2 dash, that is I2 by K. So similarly, you can transfer the primary side parameters to the secondary side. So when it has been transferred to the secondary side, this becomes R1 dash, which is R1 into K square. Similarly, when reactance is transferred to the secondary side, this becomes X1 dash, that is X1 into K square. And then I naught will be given impedance. Let us assume this particular impedance, that is no load current, is resolved into two components of a pure, having a pure resistance as well as a pure inductance. So let us assume that impedance to be Zm. So when it is transferred to the secondary side, this becomes Zm dash, that is Zm into K square, and then your current I1 becomes I1 dash, that is I1 into K, and then V1 becomes V1 dash, that is V1 into K. So this is how you'll be transferring so primary side parameters to the secondary side, or else secondary side parameters to the primary side. So when I'm transferring the secondary side parameters to the primary side, my equivalent circuit has been further reduced to like this. So which doesn't have any windings. This is my load. So this is R1, X1, R2 dash, X2 dash. This is ZL dash. This is I0. This is I2 dash. This is I1, V1. Here you can represent R2 dash, X2 dash. This is E1, which is equal to E2 dash. This is my V2 dash. This is R0, X0. So this is the exact equivalent circuit of a transformer. From which you can easily determine your impedance, total impedance, ZT. Okay, so this R1, X1 can be represented as Z1, as well as this R2, X2 dash can be represented as Z2 dash. This is my load impedance ZL dash, as well as this no load circuit can be represented using an impedance Zm. So these two impedance are in series, that is Z2 dash plus ZL are in series, ZL dash are in series, that is in parallel with your Zm. That is, the entire thing is in series with your primary side impedance Z1. So in that case, my total impedance or the equivalent impedance becomes Zm into Z2 dash plus ZL dash whole divided by Zm plus Z2 dash plus ZL dash plus Z1. So knowing the impedance, you can easily determine your voltage. V1 is equal to I into Z, I into R. So here it is your impedance, that is entire current that is flowing through your circuit is I1 into your impedance. So from the exact equivalent circuit, you can easily determine the impedance as well as your voltage V1. So further, when you see this exact equivalent circuit of the transformer seems to be somewhat complicated. In order to further reduce this or reduce the complexity, you can shift this particular no load circuit to the primary side. So in that case, when it has been transferred, so this is my I1, this is I0, this is R1, X1, this is R2, this is my load, X2 dash, R2 dash, ZL dash. So you can represent all the voltages, that is V2 dash. Here you are given an impedance. This is my E1, which is equal to E2 dash. So here R1, X1. Okay, so this is my IW, IM, R0. So this is the supply voltage V1 and this is X0. Okay, So now these two resistance can be added up together, reactance can be added up together. So in that case, I can represent R1 plus R2 dash as R01, which is the equivalent resistance referred to the primary side, and then X01 to be X1 plus X2 dash, which is the equivalent reactance referred to the primary side. So in that case, again my circuit becomes I1, this is I2 dash, this is I0, R01, X01, ZL dash, this is R0, X0, current flowing is IM, this is IW. This is the supply voltage. So, R01 is R1 plus R2 dash, X01 is X1 plus X2 dash, and this is your ZL dash. So, this is the approximate equivalent circuit. So, this can be called as the approximate equivalent circuit. So, further omitting the no load circuit, you will be getting a circuit like this. So, further omitting the no load circuit, you will be getting this particular circuit alone. So, this is the V1, R01, X01, this is I1, this is ZL dash. So, voltage across this is given to be V2 dash. So, this is the final equivalent circuit after omitting the no load circuit. Okay. Thank you.